So here is the book, and if you don't believe, I have a copy here. It's the same. Now, the book is about zonal jets. Why do we need this book? First of all, we need to know that all planets and giant planets and terrestrial planets are all featuring this long features which are jet-like, and they go normally north, east-west, but sometimes they go they have some deviation to north and south, but we all collectively call them zonal jets. On some planets, the jets are very strong, and we know them, like in Jupiter, you can watch them, and they existed them for hundreds of years, or Saturn. In the ocean, we also have zonal jets, but we don't see them. They look like a soup of eddies or some spaghetti, but they're not zonal jets. And we shall not see them until we do some averaging, ensemble averaging in time or in space. The physics of all these jets is very similar. It's not simple, but it's similar. And it also extends beyond the realm of geophysics and planetary science. It goes into plasma physics. All right. Now, what is important for all of it is a turbulence. Turbulence is a really important nonlinear process which underlies the mechanism which generates the jets. There is a very important citation which I found from Eddy. You know the Eddy problem. Everybody knows it from atmospheric science. It goes back to 1950, and this is really important to read it. He said any theory of atmospheric circulation must be based on a theory of large-scale atmospheric turbulence. Moreover, this theory must go deeper than most existing theories of turbulence. It is futile to beg the question by introducing hypothetical coefficients of eddy transfer. I have not only to establish the cause of the turbulence, but also to derive from first principles its properties with regard to transfer of heat, angular momentum, etc., and other properties. Now, all these sciences, planetary science, even within the planetary science, terrestrial and giant planet sciences, they use different jargon. Physical oceanography uses its own jargon, and plasma physics uses its own jargon. And at the end, we build something which looks like a Tower of Babel. It's a big tower and has a lot of rooms, and people cannot understand each other because they all talk different languages. So we built the Tower of Babel, but now we need a tourist guide. So this book is a tourist guide. How it all started. This is a building in Bern in Switzerland, and this is where International Space Science Institute is located. I knew about this institute because I was participating before in another program, science team, on Martian planetary boundary layer. So when I was going there, I was talking to people, how about doing something else like zonal jets? Would you be interested to entertain this? And they were positive. So I submitted proposals, and how we got funded. Bern by itself is a very interesting city. If you go to the center of the city, you will see this very nice clock tower. It's called Zeitglocke, and it has been there for a long time. Switzerland is a neutral country, never participated in any wars, never was bombed, so this thing existed for hundreds and hundreds of years. It's very famous. Every tourist goes there, goes inside, and this is a clock from the close distance. And as every Swiss clock, you see it's going, and it always shows the right time. So this is a mechanism of the clock, and this is one of the central streets of Bern. And if you go along the street this way, you will find a very interesting place. It's here. It's a house in which Albert Einstein lived. Now they made a museum out of it. So this is his living room. It's another view of it. You see the picture of him and his wife Mileva Maric. They lived here in 1905, around this time when he wrote his special relativity theory, and he didn't get a Nobel Prize, but He got a Person of the Century for this work. This is his bust, and it's a very interesting place, and it describes how it's being used and all this. So when you go to Bern, you really have very elevated feelings that you are somewhere in a very important place for science. Since this city was never really destroyed, he was working in Patent Bureau, and this building is still there. It's not Patent Bureau anymore, but you can visit and you can see the, well, I didn't go there, so I don't know if you can see the place where he was working, but the building is still there, and there is no museum there, it's just a building. So, as I said, we submitted 3 proposals, 2009, 10, and 11, and these 2 were declined, but the last one was accepted. And the reasons were very funny. It should be international team, and sometimes I had too many Americans, sometimes I had too many Brits, so the last time I had just the right combination. So the theme of this was Zonal Jets and Eddies, Planetary Science and Satellite Oceanography at the Crossroads. So this is initial cast. Leonard Benson was head of the institute, so I had to include him. I never met him, he never came to any meetings, but he needed to be there. And well, you probably know some of these people, you don't know some others. It's Pavel Berlov, David Dritchel, Stefania Espa, myself, Nikolai Maximenko, Raquel Petrosyan, Peter Reed, who was co-editor of the book eventually, Walt Robinson, Agustin Sanchez-Lovega. I highlighted their countries. Rob Scott, he was also not very active. He joined, he was in France then, but then he moved to do special relativity theory, so this was his contribution. Adam Showman, he is known planetologist. Semyon Sukharyansky is my colleague from Israel, and Bill Young is from Scripps. And to make it look even more international, you see, I needed to put Dave Dritchel as Scotland. I could have put UK, but then I would have many people from UK, so I needed to put Scotland and England, pretending that they're different countries. For myself, I was hoping that St. Petersburg will help me to look, with my name, look like a Russian rather than American. So there are some nuances here. But anyways, it was accepted. And we had 3 meetings in 2012, 13, and 14. This is our lectures. And we also had some good time after the lectures. You can see we're going to the restaurants, and they have very interesting restaurants. Usually we went in groups, but several times I went on my own. And you know, when you go to a restaurant in which they speak Swiss, it's difficult to read the menu. They don't translate to English. So once I was sitting there and I needed to order something, and I couldn't understand what the menu says. And the waitress was coming, and she was becoming really impatient. So she told me, "Are you going to order anything today or not?" So I didn't know what to do. So I said, "You know, I heard that Albert Einstein lived in this city." She said, yes, he did. So I said, "Can you tell me what he had for dinner?" So she said, "Schnitzel." Oh, I said, "It's a good idea." So it solved my problems at that time. Now, go to the book project. As soon as we got the approval of the project, we started negotiations with Cambridge University Press to do the book, because producing the book was one of the purposes of this entire proposal. The initial scope of the book was quite limited, but it was expanding as along the road, along the way, as we had more and more meetings. So it was really all-inclusive. It was the free sciences, oceanography, but even for the atmospheric sciences, we included something which is known as superrotation. Plasma physics was joined later. We didn't have it initially. We had mathematics, experimental physics, and advanced turbulence theories, of course. The cost of contributors was constantly expanding, so eventually from 12, we got to about 70. And I must tell you something about this. The way this works, you need to have a team of 12 people, you may have 13 and 14, and you can add several graduate students for free, kind of. They will be supported by the institute, by ISSI. But you need to have 3 meetings, and usually you have the same people all the time. But me being me, I thought, why do we need to have all the people, the same people all the time? We already heard them. They're not going to say much new 1 year later, so why don't we have, for the same money, new people and cover more subjects? So Swiss, they're kind of like Germans. They go straight forward, and they didn't like my idea, so I needed to negotiate with them every time. But eventually they agreed, and they were not very happy about it, but when they got the book, they were very happy to see the final product. So this is how we managed to have many more people engaged in this project, because 70 people is a really big group, and it's very, very international. So this is what we had at the end. Some of the people were not even going to our meetings, but we grew up like a snowball, and it was becoming easier and easier for us to attract new people to write the articles, because some of the subjects needed some expert input, and we couldn't have everybody coming to Bern. So on the meetings, we decided about the general hierarchy of the subjects and designated a group of authors for every subject. And it was very well organized. I'm really impressed with the way it was. I think Switzerland had a big organizing effect on the whole group. Now, the general idea was to create a fusion of pure applied and computational mathematics, geophysical and planetary fluid dynamics, experimental and plasma physics, and advanced turbulence theory, covering a broad range of subjects. And they were state-of-the-art subjects, because some of them were covered for the first time around the unifying subject of zonal jets. And the fact that we had 3 different groups all the time, I was able to bring people who were doing similar subjects in different areas, and they didn't even know about each other, because some of the subjects were just developing. And they were very happy when we put them together. They told me, oh, I didn't even know that this guy is doing similar things. And it created a lot of new papers out of this, not only the book. So it was really very productive collaboration. The chapter must be accessible to a broad community of readers, not only to graduate students, but also to experienced researchers, and vice versa, of course. Now, it was really difficult to do it in the beginning, because we had a lot of discussion. So in the first meeting, we spent about 1 or 2 hours just debating the title of the book. And the title of the book is Zonal Jets. What can be simpler than this? It took us 2 hours to get to this. So at the end, everybody wished me good luck. But it was 5 years of hard labor, and now we have the book. Now the book starts with a foreword, and this is a little sad news about the book. We wanted to come to get some very prominent scientists writing the foreword, and the first one was Raymond Hyde. He was very well-known planetary scientist, experimental scientist, working in many places, including MIT, Imperial College, Oxford, you name it. Oxford still has his big laboratory. And Peter Reed is one of his students. But Raymond got ill, his wife got ill, and it just didn't work out, and he passed away before we finished the book, so unfortunately. Then we sought to go to Garrett Williams, who was working in GFDL, and he was the first guy who did the numerical simulation of jets on Jupiter. He had a Parkinson's disease by then, and he quit the job, and he was very excited to write the foreword of the book. But then I got a call from his wife telling me that he suddenly felt very ill, and he passed away as well. So instead of forewords from these people, we got dedications to them. But at least this book is giving them a lot of respect and puts them in the right place, and it's the foundation of the whole science of zonal jets. So eventually, our foreword was written by Isaac Held, a prominent atmospheric scientist from GFDL. Now, the structure of the book, the general subjects are, well, introduction you can understand, zonal jets in nature, in laboratories, in magnetically confined plasmas, and then 2 chapters deal with maintenance and instability, genesis and maintenance of zonal jets, turbulent instabilities and some statistical theories, so it's very heavy chapters with a lot of equations, but I'm not going to write them here. And the last one was material transport and flows with jets. It's probably, I will get you very bored if I start going over it, but you need to see what we have in the chapters. The second section is really important because we have terrestrial atmospheres, oceans, gas giants, and even exoplanets and the sun. Now, terrestrial atmospheres, it's not only Earth, it's Mercury, Venus, well, Mercury, it's not that much, but and Mars. It's all planets with solid surface, okay? The oceans are a special animal which lives on Earth, and then gas giants, and it's also different kind of physics. And exoplanets, we have a lot of theories, but not much data. Then we discuss jets in several different laboratories and different experimental methods. And then zonal flows and magnetically confined plasma is kind of well, we integrated it, but it wasn't, as I told you, initially included. And the person who brought it, and he didn't produce his chapter, so we had a little problem with this. The genesis and maintenance of zonal jets is a very interesting thing because it's a collection of basic works on zonal jets. This number 12, general results on the nation in the rotating system, is a pure mathematic. It's a theorem which saying that any flow on rotating sphere has a tendency to the nation. It's just mathematical analytical result. It's very nice when we can get to this result from first principles. Now, this is all other things. There, then statistical theories are in next chapter, and the last chapter is, last section has two chapters that deal with diffusion and advection in zonal jets. Now, still have about 7 minutes, I think. So I'll briefly walk you through first several chapters because I cannot encompass everything. So the second chapter was on terrestrial atmospheres, and one of the important things, one of the very interesting things was the phenomenon known as a superrotation. So this is a vertical velocity profile on Venus. Superrotation is a phenomenon when you have very fast zonal flow developing on very slow rotating planets. One of those planets is Venus. There's not many of them. And another one is not a planet, is a satellite of biggest satellite of Saturn called Titan. They are both very slow rotating. On Venus, the length of the day is longer than the length of the year. So it takes it longer to go around its own axis than to go around the sun. It's so slow, about 100 times slower than Earth. And if you look on it, the near surface velocity on Venus is 1, 2, maybe 3 meters per second. It's near zero. But if you go to the altitude of 30, 40 kilometers, sorry, it's latitude, it's not altitude, sorry. But you can look at this here. The velocity goes to about 100 meters per second. It's, where is it coming from? How impossible that it's rotating so fast? So there are some theories which describing it, and we have it in the book. And there are some missions to Venus, and it was all measured. So we have kind of a state-of-the-art overview of the problem of superrotation. Now, on the oceans, there is evidence of multiple zonal jets, even though you cannot see them. So we start this chapter, it was coordinated by Peter Carnillon. By definition, by discussion, do we really have jets in the ocean? So he introduces 6 different science attributes of zonal jets and discusses every one of them. And the conclusion is that they are zonal jets, but you just need to know how to deal with them. So here are some examples of zonal jets in the ocean. You can see you can read this, and if you are interested, you can just borrow the book. Don't want to read all this, but you can see the strong zonal jets in the equatorial part, and you can see zonal jets here as well. Now, this is very interesting picture. This is from Peter Carnell and his student Buckingham. This is based on sea surface temperature gradient, and this one is based on ships of opportunity XBT. So you can see the zonal jets are everywhere, but they are averaged, otherwise you will not see them. Now, after the talk of Chuan Min, I wanted to see if there is any jet which can carry this stuff. Right. So if you look at it, there is a jet which can do it. It's you need to have a blue, right, negative velocity, and it goes in about right way, and it veers toward Florida. So it will be squeezed between two other jets which go to the east. But of course, it requires a little more analysis. But at least it can explain how this mechanism works. Now the jets have a property that they tend to barotrapeization, so they develop constant velocity in the vertical. So you can see that this is velocity becomes constant with depth, as expected in this area. And there is another one. It had 400 meters, the result of simulation. Also, you can see zonal jets everywhere in the ocean. And this is from Kristen earlier talk. She was talking about this surface nitride, but it also seems to be connected to zonal jets. So the transport of it is related to zonal jets. Of course, it's not log-log presentation, so you don't see the gradients around here, but you see on the poles is really aligned with the zonal jets. Now, the gas giants, we have 4 of them. We have Jupiter, Saturn. The 2 images of Jupiter. We have some analysis of it. This is a normal light, and this is infrared. So in infrared, they look really very different, spectacular. There is zonal velocity profile. You see that they're very large. On Jupiter, zonal equatorial velocity is about 150 meters per second. On Saturn, it can go to about 400 meters per second. And all these wiggles are zonal jets. We have about twice as many jets on Jupiter as we have on Saturn. The chapter discusses different phenomena on Jupiter, like great red spot and ovals and some giant storms on Saturn, the hexagon on the Saturn pole. So it's a very interesting chapter, and it's state of the art. It goes all the way up to the Juno mission, which was just finished, still going on, but it was just kind of summarized last year. This is Uranus. It's a very interesting planet because it rotates, the axis is horizontal. It rotates like this, not like all other planets. And this is the zonal velocity profile. Unlike Jupiter and Saturn, the velocity profile on Jupiter and Saturn velocity is eastward. On Uranus and Neptune is westward, and there is no explanation why they have different directional equatorial flows. So this is Uranus, and this is Neptune. You can see this. And now, this planet developed something which is known as a Suomi effect, which means that he questioned how come the Neptune is the farthest away from the sun, but it has the biggest velocity. If you take the difference between westward and eastward velocities, it's about 600 meters per second. It's a huge velocity. Now, we have a theory which is called anastrophic turbulence, which can explain this. So, we discussed it in the conference. We also talked about jets in the laboratories. There are different devices. I would like to mention this particular device by Yakov Afanasyev in Newfoundland. It's laboratory altimetry. So he puts a light source over the rotating tank. So he has jets and flows here. And then he measures its surface elevation gradient with very fine technique. And he can, like at satellite altimetry, he does the same in the laboratory, and he can extract the flow field from satellite altimetry. Okay, another thing, this is with Stefania Espa in University of Rome. This is a work which we did with my former student, Jesse Homan. This is the pictures which he produced. So it was forced by magnetic field, and you can see this is like Earth. Instantaneous picture has not much of a jet, but a lot of big eddies. But when you average it, then you don't have any more eddies, but you only have the alternating zonal jets. So this is a way to imitate what is going on in the ocean. Another picture, this is what started all this. We did the comparison of the simulation of the North Pacific and Jupiter, and this is when we first found alternating zonal jets and published the paper, which then stimulated some research. What was important that we explained it by xenostrophic turbulence. It's a term which we introduced, and it was used a lot in this book. So it was also gratifying for us that it picked up with a scientific audience. Now, very important thing was later on when I got this email from Karl Wunsch. He said, Boris, I took the book to Woods Hole for a month. I cannot say I read it through. That's a bit like trying to read an entire encyclopedia. It's very well done, and I think it will be standard reference for many years to come. A great job. So this is my last slide, and now we're very proud for this book and for this message from Karl. And